In this video series, I will demonstrate the forging of a katana from a section of steel cable and a railroad spike. Although these may seem like strange starting materials for making a Japanese sword, there is actually good rationale for their selection. Both the cable and the spike are made of unalloyed, plain carbon steel. The cable has just under 1% carbon content, while the railroad spike has around 0.4%. Traditional Japanese swords are crafted in such a way that they have a softer, more flexible core enveloped in a hard outer jacket. And as it turns out, the outer jacket of a traditional katana is very similar in chemistry to the steel cable I will be using, while the core is very similar in chemistry to the railroad spike. What's more, in addition to the chemical and physical properties of the steel, the wires in the cable will produce a visible pattern in the metal, which, after the folding process you'll see demonstrated here, should look similar to what's seen in traditional katanas. Before proceeding with my project, let's just briefly review the traditional method for forging katanas. Japanese smiths start with a very primitive steel, known as Kawagane. Contrary to martial arts mythology, this steel is inferior to most modern steels in any measure of performance. However, it does possess one important quality that has made it useful for sword making over the centuries. Since it is smelted at relatively low temperatures, it does not form alloys. This makes it a pure, plain carbon steel and gives it very predictable physical properties. It is also said to possess unique aesthetic qualities. Japanese smiths start by heating chunks of the raw steel and then flattening it into thin discs. While still glowing hot, the discs are quenched in water, which causes them to harden to varying degrees, depending on their carbon content. Afterward, the discs are broken into smaller pieces, which are sorted based on how easily they broke apart and the appearance of their broken edges. Pieces with a carbon content of around 1% will become the outer layer of the sword, while those with between 0.3 and 0.5% will become the core. Pieces are stacked together on top of a plate made from the same Kawagane steel, which is attached to a long handle. The stack is then wrapped in paper and covered first in straw ashes and then a clay slurry. The clay slurry acts as a type of flux, preventing excessive oxidation of the steel pieces. The silicates in the clay actually melt, forming a molten glass layer over the steel. In this shot, the clay can actually be seen bubbling like hot butter on the surface of the stack. Once the stack has reached a bright orange-yellow color, it is removed from the forge and given gentle taps to begin the process of fusing the pieces together. The stack is then returned to the forge, reheated and hammered again. With each repetition, the force of the blows increases until the stack is condensed into a single solid block. In the next stage, a cut is chiseled into the block, and the steel is folded back over itself. The two-layered block will then be hammered out and folded over again. Each time the folding process is repeated, mineral impurities are driven off by the hammer blows. But maybe even more importantly, the block of steel is homogenized, the process being not unlike kneading bread dough. The entire folding process normally involves between 12 and 15 folds, creating anywhere between 5,000 and 30,000 layers per centimeter of thickness of the refined finished steel. These layers generate a visible pattern in the finished piece and constitute an important aesthetic feature of Japanese blades. Alright, that's enough of a review for now. Let's look at the project at hand. I started with a pretty low-tech approach to forging cable, one which could probably be done by anyone with a hammer and a forge. I used 1-inch diameter cable because anything much larger than that is exhausting for one man to forge alone. I begin by wrapping 12-gauge steel wire around the cable, about 1 inch from the end, and twist it tight to prevent the cable from unwinding. I place a second piece of wire about 4 inches from the first. Then I cut the cable about an inch from the second wire, making a piece of cable about 6 inches in length. Then I place the piece of cable in my propane forge, which I've lined with extra fire brick to protect it from the erosive action of the borax flux, which you'll see in a moment. Now there's a bit of controversy about how cable should be treated before forging. Steel cable is coated in an extremely thick, sticky lubricant, which is nigh impossible to remove with soaps, detergents, or solvents. I've handled cable with my bare hands in the past and then been unable to completely wash the lubricant from my hands for a couple of days. Different smiths who work with cable have different elaborate methods for removing the lubricant, all of which I believe are unnecessary. See, the lubricant is some type of petroleum product which can simply be burned off. At first, the lubricant catches fire and burns, like all petroleum products. And by the time the cable reaches the screaming hot temperatures required for forge welding, the lubricant will be nothing more than atoms floating on the breeze. Any carbonized residue remaining on the cable is easily removed by the borax flux. Once the cable is glowing red, I coat the piece liberally with borax. Then I return it to the forge. Once it has heated to a bright orange, I coat it with borax a second time and return it to the forge to soak for a minute or two. Here the borax can be seen bubbling on the surface of the cable, much as the clay could be seen bubbling on the Kawagane stack earlier. The liquid borax is quite acidic, and it is this soaking of the cable piece in the bubbling hot borax that removes any carbonized lubricant. After a minute or two of soaking, I place the cable in a vise, grasp it at the end with channel lock pliers, and wind it as tightly as possible. This partially fuses the strands in preparation for hammering. If this step were skipped, the process of hammering would unwind the cable rather than condensing it into a solid bar. After 30 seconds of reheating to bring the piece back up to bright orange, the cable is taken to the anvil, where it is tapped gently to further set the welds between the strands. A second round of gentle taps continues the process of forge welding. Once I can feel and hear that the cable is becoming a solid piece, I increase the force of the hammer blows. After 3 or 4 heats and a couple of minutes of hammering, the cable has been fused into a solid bar. Now I form the round bar into a flat, rectangular bar, and the gentle taps are replaced with much more forceful hammer blows. Here is the rectangular bar formed from the first piece of cable. I have cut it in half and sanded the end to demonstrate how perfectly the strands of cable fuse together. To all appearances, it is a single, solid, uniform bar. Any pattern created by the individual strands would only be visible after polishing and etching. Now at this point in my project, I hit a barrier. I used the method I've demonstrated to make 5 bars from pieces of cable, and my idea was to forge weld them into a single lump that I would then cut and fold the way traditional Japanese smiths do. But after one evening of experimentation, I found that I was simply unable to generate enough force with my right arm and my 2.5-pound blacksmith's hammer to move that much metal. There's a reason Japanese smiths work in teams of 3 or 4 with apprentices swinging 20-pound sledgehammers, and I realized that I was never going to be able to accomplish the same thing by myself. So, I took a little break from blacksmithing and I built some gadgets to aid me in my project. The first was this 20-ton press. It was actually made by a good friend of mine, Tom Dobiecki, who is an engineer, amateur machinist, tinkerer, and general builder of things. I lent a hand here and there, but mostly watched as he made this press from scratch. Then I built this Dawn Fog-style vertical forge. This I did make myself, although I can't take credit for the design, which I borrowed from various sources on the internet. I absolutely love this forge. It's tremendously more efficient for almost every purpose than my previous forge. Someday I plan to make a short video about the forge, how I made it, and what it's good for. I also invested in this Lincoln Electric stick welder. I used it to assemble my forge, and I also use it in various steps of the forging process. The first thing I did with my new toys was fuse those 5 bars of cable steel together. I used my stick welder to weld the bars together along one end, and then I welded a rebar handle to the stack. I heated the stack in my new vertical forge and then used the press to fuse them together. Note that although the press is capable of generating much more force than I show here, I begin with gentle squeezes, just sufficient to weld the bars together. Once I had played with my forge and press a little, I got an idea of how I might use them to work efficiently with larger pieces of cable, pieces too large to work with a handheld hammer. I needed quite a bit more steel than those original 5 bars, so I decided to try this new method to see if it would be a more efficient way of making larger bars. I took a piece of 1.5-inch diameter cable and welded the ends together to prevent it from unwinding. Then I welded a rebar handle to it. I placed it in the forge and burnt off the lubricant. Coated it with borax flux, and allowed it to soak in the borax until it reached a bright orange-yellow color. Then I put it in the vise and wound it as tight as I could. After a 30-second heat, I took it to the anvil and set the weld with a series of gentle taps. So far, this procedure is about the same as with the smaller diameter cable, but here is where it gets different. After the welds were set with the hammer, I put the cable in the press with the squaring dies in place. The tremendous force of the press condensed the heavy chunk of cable into a solid bar in mere seconds. A second heat and the press finished squaring the bar, accomplishing in about 1 minute a task that would have taken me at least an hour of exhausting heavy pounding with my hand hammer. From this point, I immediately went to drawing out the square bar using my drawing dies. These cylindrical dies force the bar to expand lengthwise without increasing it in width. Since they concentrate the force on a relatively small surface area, they mash through the steel quickly and easily. After each pass through the press, I vigorously brush the oxidized scale from the bar to prevent it from being worked back into the metal. Then the flattening dies are used to flatten the high spots left by the drawing dies. This alternation between drawing dies and flattening dies results in fast and efficient compression, since the force generated by the press is always applied to a small surface area. The entire task could be accomplished with the flattening dies alone, but it would take longer. Once the bar has been flattened, squared, and prettied up, it's time to make the first fold. Before folding the steel back on itself, I hammered a bit on a wet anvil. The water evaporates explosively, cleaning any scale or debris from the surface of the metal. I sprinkle a little borax over the union between the two layers to prevent oxidation and assure a good weld. And then after a short heat, I take it to the press and set the weld. After another heat, it's back to drawing and flattening. Then another fold, and the process is repeated. In total, I folded the bar 10 times, resulting in 1,024 layers. And here is the resulting bar after a quick pass with a flap sander. Notice that there are no bad welds, inclusions, or any other defects present. It looks like a solid bar of uniform steel. Also notice that it is less than half the size of my original bar. This is because some steel is lost as oxidized scale after every heat. I will now repeat this process with 2 or 3 more pieces of cable in order to have enough steel to make a sword.